Hello my friends, and welcome with you again with this new series, the Postgresql Indexes. In this video we will talk about the types of the indexes and their operators. The first thing we will talk about the types is, of course, how many types. There are about 5 or 6 types in PostgreSQL. The first one is the B-tree, and then the brin, and then the gen, and then the gist, and then the spgist, and these are the most important types of indexes. Now, the B-tree is the default index type that PostgreSQL uses, and in general B-tree covers almost 95%, or let me say 90% of the usages of the indexes. So if you use B-tree, it can cover almost all your usages of the indexes in PostgreSQL. The rest of the usages for your requirement, when you do an index requirement, you will use some of brin, which is the block range index, as well as probably the gen, which is also another type of the index. But mostly it is the B-tree, and it is by default, it is the default type of index that PostgreSQL uses. So when you do an SQL query or when you create an index, you don't have to mention that you will use the B-tree index type, because by default, when you create an index in PostgreSQL, the B-tree is the default type. Okay, so in any query planner, it will consider using a B-tree, as we have said, whenever an index column is involved in a comparison using one of the following operators. So what does that mean? This is the operators that belongs to the B-tree type, the index B-tree type, which means if you create an index, this is the index which I have created now. This is the syntax of when you create an index. Create index, the name of the table. By definition, the name of the index consists of the table name, the column name, and IDX, which is the name of the index. But still, you are free to use whichever name in this case, whichever name for you. But this is the convention. The convention is that you mention the table name, then the column name, then the IDX. Then we will write the keyword on and the table name, and then the column that we wish to create an index on it. Now, when we do any query on this table, when we do implement any query on this table, whenever the query planner sees any of these operators, that he will know that you are using a B-tree index. So for instance, in this select query, there is bigger than operator. Now, bigger than operator is one of the operators that belongs to the B-tree type, B-tree index type. That means the query planner, which we will talk later on about, you will understand what is the query planner. The query planner will recognize that you are using a B-tree index whenever it uses C greater than operator. So when the query planner see any of these operators in any select, in any query, whether it's a select, delete, update, whenever the query planner see any of these operators in any query, in any SQL query, it will recognize that you are using, or it will select for you, a B-tree index to implement your query. So these are the operators, and these are the conditions for each and every operator that you will use in your query, in your SQL query, whenever you want to implement on any table. So in brief, first index type is B-tree. It is the default type for PostgreSQL when it implements any SQL query, and it consists of these operators. Whenever any of these operators appear in any SQL query, then the query planner will recognize that it will use the B-tree index type on this SQL query. Let's go for the second type of indexes, which is the BRIN. The BRIN is an acronym of Block Range Index. Block Range Index. The BRIN is good for the large tables. The BRIN index type is good for the large tables. Now, each few pages that are adjacent to each other can be grouped in a block. This is the concept of the block range index. If you have a big table, hundreds of thousands, maybe millions of rows, these rows are all placed in pages, so pages are adjacent to each other. The block range will group each few pages that are adjacent to each other and put them in a block, and accordingly would divide the number of the pages that are available for this table into a certain number of blocks. Now, you might say how many blocks will be for this table. Now, this can be decided by this function, which is pages per range. Pages per range. Whenever you create the index, the BRIN index, this pages per range will decide how many pages or how many blocks it will create, and accordingly will divide the number of the pages in these blocks. Now, each page, of course, consists a certain number of the rows, of the tuples. Now let's read this phrase and then we will talk about what's the meaning of it. The smaller the block, the larger the index size. The smaller the block, the larger the index size. At the same time, the summary data stored, the summary data means the data in these rows, in these tables, in these rows, stored can be more precise and more data. Blocks can be skipped during the index scan. So, when I create a smaller block, the size of the index will be bigger, but at the same time, if I need to check or retrieve a data in a certain place, in a certain block, in a certain row, because I have many smaller blocks, I will go to that block directly instead of searching bigger blocks. We will see this in a minute. What does that mean? Suppose that we have this column. This column consists of salaries, let's say 100,000, from 1,000 to 100,000. These are the amount of the salaries. We will block the salaries, the rows of the salaries in blocks. So from salary 0 to salary 1,000, we will put them in block number 1. From salary 1,001 to 1,500, we will put in block number 2. Salary 2,001 to 2,000, from 1,501 to 2,000, we will put in a block, and like so we will do this. So each range of salary amount, we will put in a block. So keep that in mind. Now, this will create blocks for us, and each block, as we have said, contains a certain amount, a certain number of pages. So for instance, this what we have just did now create for us these pages. So all the numbers that available here in the salary columns have created for us these pages, and now we need to divide these pages into blocks. So we will divide we will place the first 5 pages in the first block, second 5 pages in the second block, third 5 pages in the third block, and so on. So if we have 20 pages, that means we will have 4 blocks. Now, if we have 25 pages, we will have 5 blocks. In each block, we will have 5 pages. Now, what if we have decided to create blocks that contains 3 pages instead of 5 pages? So we have 25 pages, in each block 5 pages. Now what we need to do is to make only 3 pages in each block instead of 5. What does that affect? How it will be affect? What is the effect of this decision? In this case, if we have 5 pages per block, the summary index size will be 3, which means the size of the index will be 3 blocks. The summary's index size will be 3. But if we have to choose, we have elect to place 3 pages in one block. That means we will have 5 blocks, 5 summaries index size. The size of our brain index will be 5 instead of 3, because we placed less pages in each block. From 5 we have 3 blocks, summary index size. We now have 3 pages in each block. That's why we have 5 summaries index size. Now you might say, okay, that's not good because now the index size is bigger, right? Which is not a good thing. Yes, that's true, but there is another positive side. There is a positive side for this. Although the bigger the size of the index is a negative side, but there is a positive side for this process, for this thing. As we have said before, if we have a data, now this is a block. We have an information in the page number 3. We need to retrieve this information which is available in page number 3. Now, with this index, with the first index, we need to go through 5 pages, search to find the data that we are looking for, which is available in page number 3. This will take some time, of course. Now, what if we took the second type? Now we have only 3 pages. 3 pages only in each block. And our data that we want to retrieve, it's available in page number 3. As you think, and that's the case, the search will be faster. The search on our data will be faster because now we are searching less blocks. We are searching less tables. And that's the benefit. Although we are increasing the size of the index, but at the same time, this is a negative thing, but at the same time, the size of the index or the number of the pages that we have to scan in each query will be less. Therefore, our reach, our retrieval of the data will be faster. So it's a trade-off. It's a trade-off. You need to see whichever formula is the best for you. Is it to increase the size and put many tables, put many pages in a block, or do the inverse? So this is like a trade-off between the size of the index and the speed of the query. As we have said, in general, the brain index, the block range index will be applied on the big data, on the big table, on the big tables. And there is one very important thing when you want to apply the block range index. The data of that table should be sorted. It must be sorted before you do any scanning, before you do any querying, before you do any search. The data must be sorted. It has to be sorted, otherwise you cannot, it will be useless to use the brain index. It will be totally useless to use the brain index on your table if your data is not sorted. Now let's see about the third type of index, which is the GIN index. The GIN index it will be used in cases where the items to be indexed is composite values, and the queries to be handled by the index need to search for elements values that appear within the composite items. I'm sure, I assume that you know what is the meaning of the composite values. So if you have a table with composite values, then the GIN index is what you're looking for. It is much better to use the GIN index rather than the B tree. And these are the operators that is applied on the GIN index. Whenever the query planner see any of these operators, it will immediately select for you the GIN index. And you can have a lot of details about it in here, in these two links. The fourth index, which is the gist, this works for the two-dimensional geometric data types. I believe that like for in the maps for the gist, PSGist also it is working for it. So any two-dimensional geometric data types, the gist will be your decision to choose. And these are all the operators that works with the gist index, and these are the links where you can find all the data about this index type. Now these are all the most important index types which we have spoke now. But as I said again, the B tree is covering 90% of whatever your requirements. So whatever your requirement on any SQL query, B tree is almost your target, and it's by default. It is the default type of index that can be used on any SQL query, unless you have the other types that we have spoke, other requirements, then you can use the other types of the indexes. Thank you very much.